This is 12.3.5 mass and energy. So last time we looked at two phenomena that happens when objects approach close to the speed of light, which is time dilation and length contraction. The final thing is that when objects move close to the speed of light, their masses increase. So mass increases as velocity increases. So if we have some object that's moving at velocity v, then it has a mass m. M is its increased mass when moving at velocity v. And they also have a rest mass, which is when they're not moving, and we'll call that m naught. So, a moving observer will observe the masses of objects to have increased if they're moving quickly. So according to a moving observer, mass increases, and the equation we have is m is equal to m naught gamma. So if we substitute the values for gamma into there, we've got m equals to m naught over square root 1 minus v squared over c squared. So as you give objects energy, normally we say that their kinetic energy just increases. But when we're talking about extremely fast speeds, then their mass also changes. At that point, we can't use the kinetic energy formulae as they are. And you'll see that certain other equations we've been taught recently stop working as well, when you have to take into account of relativistic effects. So let's start a new page. How increased energy changes mass. So let's think of the electron gun equation. QV equals to half mv squared. If the mass of an object did not increase with velocity, then some values of potential difference could give us values of velocity greater than the speed of light. So if we made v very, very large, then we could get a value of small v, the velocity, that's greater than the speed of light. But we know that things cannot move at or faster than the speed of light. So this equation does not hold true at fast speeds because values of voltage can result in V greater than C. Right. So now we have to think about energies and kinetic energies in a different way. If you give something energy, you do two things to it. You increase its velocity, but you're also increasing its mass. So you're affecting its total energy. So at the start, your object is at rest, so it has rest energy. There's a C there. So your rest energy is E equals to mc squared. But remember, we're using the rest energy, so it's m naught c squared. And because the rest energy, we'll also call that E naught. So the original energy. Now, if we apply some energy to this object, we give it some energy or some heat, and it starts to move extremely quickly, then its energy changes. So give object energy, and its mass changes because of the energy you give it. So its mass changes to m. So energy, E1, is now equal to mc squared. The energy that you've given it is the difference between its new energy minus its original energy. So the energy gained is the difference of new and original energies. So the gain of energy, the delta E, is equal to mc squared minus m naught c squared. I'll put a bracket, a box around that. So for example, if a particle, like a proton or an electron, is accelerated through a potential difference, e.g. like the electron gun equation, then the gain of energy is still QV, but the gain of energy is not equal to a half mv squared anymore. It's equal to the difference of mc squared and m naught c squared. So a particle is accelerated through a potential difference V. So then what we do is we say that the gain of energy, delta E, is equal to mc squared minus m naught c squared. So QV equals to mc squared minus m naught c squared. So the question could ask you to calculate the velocity that this particle moves in. If question asks for V, then sub in m equals to m naught gamma. So if we do that, we've got QV equals to mc squared, but instead of m, we're going to put m naught gamma. So m naught gamma c squared minus m naught c squared. Then we can put the value of gamma in. So we've got QV equals to m naught over square root of 1 minus v squared over c squared minus m naught c squared. And if we want, we can factorize that. So QV is equal to m naught c squared into 1 over square root of 1 minus v squared over c squared minus 1. So at that point, we can just rearrange it until we find v. Okay? So let's do an example together. So we have an electron is accelerated through 10 megavolts m naught for the electron is 9.11 times 10 to the minus 31 kilograms. So number one, we calculate the gain in kinetic energy. Number two, we're going to calculate the mass of the electron in terms of m naught. And number three, we're going to compare its velocity with c. Which basically means find v over c. So let's do the first one. To answer question one, we need to find the gain in energy. So the gain in energy is just equal to QV. So that's 1.6 times 10 to the minus 19 times by 10 times 10 to the 6 volts. That gives us the gain in energy as 1.6 times 10 to the minus 12 joules. For question two, we then write the energy in terms of its change in mass energy. So EV or QV equals to mc squared minus m naught c squared. We bring the c squared to the other side. So EV over c squared is equal to m minus m naught. And then we move m naught over to find its new mass in terms of m naught. So m is equal to m naught plus EV over c squared. And then finally, we want to find V over C. So using this, we're going to put the equation into M, which is m naught over square root 1 minus V squared over C squared. So m naught over square root 1 minus V squared over C squared is equal to m naught plus EV over C squared. I'm going to multiply the square root to the other side. So we've got m naught is equal to brackets m naught plus EV over C squared, close that bracket, square root of 1 minus V squared over C squared. We'll then divide all of this term to the other side. So m naught over m naught plus EV over C squared is equal to square root of 1 minus V squared over C squared. Square both sides to get rid of the square root. So we've got m naught squared over, put brackets, m naught plus EV over C squared, brackets squared, is equal to 1 minus V squared over C squared. Rearrange to put V squared over C squared on one side. So we'll bring that to the left and bring all the left terms to the right. So V squared over C squared is equal to 1 minus m naught squared over brackets m naught plus EV over C squared brackets squared. And then square root the entire thing to get V over C. One minus m naught squared over m naught plus EV over C squared squared. And that's given us V over C. So there's a lot of steps involved. There's a lot of algebra involved. But the key points are, you don't use the kinetic energy formula anymore because mass is changing. The kinetic energy formula only holds true if mass is constant. But if we know the mass is changing, then the change of energy, so the energy given to the object, resulted in its mass to increase. So its change of total energy equals mc squared minus its rest energy m naught c squared is equal to the change of energy, and then you evaluate from there. Let's move on to the final thing. So starting a new page. This is Bertozzi's experiment. So first I'm going to give you some graphs. So I'm going to give you a graph of m over m naught and kinetic energy Ek. So if we put m over m naught on the y-axis, and we put v over c on the x-axis. When v is equal to c, so if velocity is equal to speed of light, that will give us 1. So when v is equal to c, that gives us 1. And this value is an asymptote. When m is equal to m0, that also gives us 1. So the lowest value we can have here is 1. And the graph looks like that. It's asymptotic. In the classical approximation, where mass does not increase, so this is relativistic, and the classical, I should probably change colors for classical, so let's change to blue. So the classical approximation will just be a flat line here. So the classical says that no matter how fast you're going, the mass doesn't change. So it's a flat line. And if it's a flat line, we can see that classically, it's possible to say that things can move faster than the speed of light. But we know that doesn't happen. Then for kinetic energy, we put EK, and we put velocity here, and we'll label here as speed of light. The relativistic approach gives us a function that's asymptotic again, which means that we can never reach the speed of light because it will take infinite energy. But the classical approach would give us a quadratic function instead. So the classical suggests that because it's a quadratic function, half mv squared, that if you just keep increasing the energy, then v will continue to keep increasing as well. So we'll look at Bertozzi's experiment. So this is a sketch of something called a linear accelerator. You don't need to know exactly how a linear accelerator works, but it's basically a particle accelerator that accelerates electrons in a straight line using electric fields. So the electrons are accelerated for about 1.5 mega electron volts. The entire apparatus has a distance of about 8.4 meters. So it's somewhat large, but not extremely large. And on the end here, you have an aluminium disc or plate. So what happens here? Electrons are emitted from the filament using fermionic emission. The electrons are then accelerated through the linear accelerator, the LINAC. So we can label this part here as the LINAC, which is short for linear accelerator. So they accelerate through the LINAC through using electric fields. So the electrons gain some energy. When the electrons are incident with the aluminium, they're absorbed by the aluminium, and so their energy is absorbed by the aluminium plate. When that energy is absorbed, the aluminium plate heats up. So we can measure how much it heats up and calculate the energy that it's absorbed by using mc delta T. Then the electron flight time is calculated using the oscilloscope connected, because every time electrons hit the aluminium, we get some signal in the oscilloscope. Because we know the distance and we know the time by using the oscilloscopes of how long it took the electrons to reach the end, we can calculate the speed of the electrons. And then we can put these into a graph and see how it compares to the theories. So we'll just bullet point all of those points one more time. So electrons are emitted through fermionic emission. Then the electrons are accelerated through the linear accelerator. Using E fields. And if you use E fields, then you can calculate the energy that's gained by the electrons as well. But that can be quite difficult, especially if you're using very complex equipment with lots of stuff going on. So electrons hit the aluminium plate or disc, and by hitting it, it heats up the plate. So I'll put in brackets here that EK of electrons goes to E heat. So the energy is calculated because you can calculate heat. And then the electron pulse flight time can be measured using the oscilloscope. Then finally, the graph is plotted. So on the y-axis, we put v squared over c squared. On the x-axis, we put ek over m naught c squared. The relativistic approximation gives us something that looks like this. So this is special relativity. Then the classical or Newtonian approximation gave us this. And then the actual experimental results gave us data that looked like this. So the results from the experiment were in agreement with special relativity. There's very little difference. And it followed a similar function, but didn't follow the classical or the Newtonian approximation, showing that special relativity did work experimentally as well. And that's the end of 12.3.5.